I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Good afternoon. Not sure how many of you would like to watch, have the I would say the hobby of like watching TV series, but you know, like once a while, those TV series they would like come back again, like season 1, season 2, and before the new season, they usually would start with a review on what happening in the previous season. So today is also a review, not just before the midterm, but also before we start a new season of computer architecture class. But so enjoy it, right? So for the sorry, it's not moving. Okay, so first of all, right, I want to say like the most important thing, right? So the most important thing in computer architecture is to know this, right? This big picture we have. So the big picture we have in our computer architecture is that every computer that you are using right now is a so-called von Neumann computer, in a way that the computer contains processor, memory, and storage device. And whenever you want to launch a program, the program must be firstly compiled or presented in machine code, and the data that we need are presented in the encoding that the computer can understand. They must be well laid out in your storage. Or if you have other approach of generating the program and the program data, they must be presented in the memory before the processor can execute it. And the processor will execute the instruction, execute the program instruction by instruction. And according to what type of instruction it is, sometimes we might need to access memory and sometimes we don't. And if the instruction has a new result, we would update it into the register within the processor. And after the instruction is done, we will move to the next instruction. So that's the basic idea of computer architecture right now. And the good thing about this behind this big picture is that as long as you can load different programs into the memory, your computer can perform different functions. So that's how the foundation of software would work, is that right now you don't have, well, in the past, if there's no von Neumann architecture, there's no way you could compose a program. You can just compose a program and the computer will perform differently. Instead, you have to always reconfigure your hardware. So because this architecture is so important, it's also important for us to see how does a processor to execute instructions, so that you know why instruction set architecture is so important, why the performance equation like this, right? So first of all, the very first stage in the processor to execute an instruction is to fetch the instruction. So every instruction would implicitly have a memory access from the memory location pointed by the PC. And the PC means the program counter. So first of all, no matter this is a memory instruction or not, you have to fetch the instruction from the memory. So that's the very first memory access you would have in von Neumann architecture. And then after we fetch this instruction, we can decode it. And when we say decode, it means that we want to figure out what the instruction is doing. And when we say what the instruction is doing means like where are the operands and what's the desired operation. And except for memory instructions, their operands should all, well, actually, except for load instructions, all the operands should come from register values, right? So an instruction can leave or say can go to can leave its instruction decode stage, go to another stage only if the source register values are ready for the instruction to use. And the next stage is execution stage. And depending on what the instruction is, if it's an LU operation, then we just use the LU to perform the arithmetic operations or logical operations. If it's a conditional branch, means that you need the LU to present to calculate the branch outcome. Otherwise, there could be memory operations that you still need the LU to calculate the effective data memory address. So that's the execution stage. And if it's a memory operation, memory instruction, we also need to additionally access the data memory using your LU outcome as the memory address. So a lot of you keep asking me about, hey, so like, isn't there a structural hazard or data hazard associated with the memory address that store instruction associated with the memory address field, the base register in the store instruction? The answer is no, because what you really store into is where the LU outcome calculated using that register. So after you are done with the execution stage, the store instruction is not depending on that register anymore. In other words, because we just use that as the source to calculate the memory address. So we don't. It's not really a destination. So that's the clarification I think you guys must keep in mind. And then after we are done with that, we can write back the result of an instruction and as well as updating the PC. But when we say updating the PC, there are a few different things you need to take care. So first of all, if it's a branch instruction, if the branch is taken, it's set to the branch target address. Otherwise, you just go ahead and to PC+4. So that's the life of an instruction in a processor. So because the processor is made to execute instructions, so the instruction set architecture is very important in a way that it gives the contract between the hardware and software. And it abstracts the underlying processor by exposing the available operations that the processor can execute. And it also defines the memory space because, as we said, the von Neumann architecture is basically processor and memory. So that's what instruction set architecture would define. And by writing your software on an instruction set architecture, you don't need to worry about what kind of hardware circuit that we use to implement the instruction. You don't care what kind of processor you are doing. You just need to know that, okay, I have a processor support this instruction set architecture. So an instruction set architecture usually typically includes instructions and architectural states. When we say architectural states, they are registers, memory locations, memory content, and program counters. So with instruction set architecture, it basically providing you an abstraction that you don't need to worry about what's inside that processor. All you need to know is that this is an x86 processor, or this is an ARM processor, or a RISC-V processor. And what you see is just this available registers and operations that you can use. So in CSE30, a lot of you learn about like assembly language. A lot of you learn a lot of optimization techniques using assembly language, although later on in our class, you know, a lot of them are probably junk now. But the one thing that I want to mention about the assembly language is that most of the time, right, in my class or in our homework or in your test, we only show you assembly language. It's not because assembly language is something the machine can understand. It's just because assembly language has a direct mapping between assembly code or say machine code instructions. So so say usually when we write an instruction, you should imagine that we meant to say this thing, right? We just want you to easily understand, okay, this stuff representing this stuff, but doesn't mean the assembly language is something that the program can, the processor can directly accept. Okay, so right now we are going to talk about the instruction set architecture that we use the most intensively in a class. That is the MIPS instruction set architecture. So for the MIPS instruction set architecture, it defines a memory space, and the memory space has up to 2 to the 32 bytes that you can use, and it starts from 0 to 2 to the 32 minus 1. So some of you might be asking like, okay, if I want to allocate an 8 GB memory location in MIPS 32 architecture, is that possible? The answer is no, because this is the upper bound memory location you can use in MIPS. But for x86, there is no such a restriction because right now it's 64-bit architecture. So within the processor, there is a program counter. However, you cannot directly access the program counter. What you can directly access are those registers that are general purpose in a way that, except for the zeros register, who always return 0, and no matter what you do with it, other registers you can directly read with any instructions that you have. And each of the register is a 32-bit wide register. The processor has an ALU support these operations that you might already learn later. And whenever you need to execute an instruction, we just go through the address that's pointed by the program counter. And if you want to access the data memory, you have to use load store instructions. So that's the summary of MIPS instruction set architecture. It has 32-bit registers, so everything is about 32. 50 operations, which require you to use 6-bit to encode it 3 different instruction formats. So it's pretty simple. Why am I saying this is simple? Because later on, when we talk about review on x86, you will know like it's completely different. So again, right, for this class, I am not asking you to memorize all the MIPS instructions. And for many CSE141 class offerings, they require you to write a lot of assembly code in a test. We do ask you to write assembly code in assignments because I just want to force you understanding what's the relationship between assembly and how to and what's the meaning of each instruction in MIPS instruction set architecture, so that later on in the class we have we are all on the same page. When I say load word, you know what the load word instruction is doing without keep asking me why this is like why we have to activate this part of hardware or why there's such an issue, right? But being honest, I only ask you guys to see this very few set of instructions, right? So just try your best to take a look at the table, right? Because this is all you need to know in my CSE141, not other people's, right? So I already made it simple, right? But so one thing that I really want to emphasize again, because I got people asking about this question again, is about the load store instruction. And again, see what a load word is doing is that we assign the value of register from the memory location, right? So the S2 is a source. This is a target, right? And for store instruction, we access memory as well. And the memory address is S2 plus 4. So S2 is a source. And the memory location value should then be S1. So S1 is also a source. So store instruction, nobody should depending on it because there is no destination. There's no destination register in store. So again, right, if you have a question, if you have a question, asking you about like data dependency or data hazard, and if you have something, you have a data hazard or data dependency because of you are waiting for something from store word, trust me, you are on the wrong track. All right, so just one thing that I want to tell you. And the same thing for branch instruction, all of them are source registers. So if you have anything with data dependency because of the branch instruction, you are also on the wrong track. Okay, so it's important for you to figure out the programmer level meaning of assembly instructions. So so it's also important. So you should be able to know like how to translate the C code into the assembly. And sometimes if you know this mapping, it's easier for you to figure out the implementation in software level, so it's easier for you to analyze. For example, if you just look at this, right? If you just look at the assembly code, if I'm asking you to analyze the behavior of branch prediction, then it's probably hard, right? But if you know this is a C code, then it becomes easy, right? So if you have this translation, it's also not too hard for you to figure out how many branch instructions are there in your loop to estimate like the branch accuracy, branch prediction accuracy, or the CPIs for your instructions, right? So so that's why this is important. All right. So another thing, right? So when we say instructions, sometimes we are asking about dynamic instructions. Sometimes we are asking about static instructions. So here is the definition of static instruction. It's the instruction in a compiled program. And dynamic instructions are represent how many instruction instances are there in the executed program, or say the programming execution. So these are different concepts, right? And another thing, right? So for modern programs, we do have a lot of function calls, right? So, but if you just use the function call instruction, is not sufficient. And a lot of you, not sure what kind of programming language or say what kind of assembly language you learn in CSE30, I found a lot of you feel, well, the processor will automatically deal with the function calls for us, but I don't think that's true in general. And even for x86, you need to push and pop. So, but in MIPS instruction set architecture, we don't have push and pop instructions. So what you have to do is that you have to explicitly add code to emulate the software maintained stack in the memory. So that's why you see for the function code, we have to add some preambles and post sequence here to deal with the memory stack in the system. So that's what why we need this additional instructions in your code when you implement a function. So sometimes some people were asking me about like, okay, professor, you are asking me to implement a function. Do I need to include this? The answer is yes, because this is a function. We have no idea who is going to use it. And what to store, the high-level guidelines that if that's something I'm going to overwrite in my code, I have to store. So say like here, if you look at your application code, I'm overwriting A0. I'm also writing I am overwriting V0. I'm overwriting if I'm calling another function, I'm overwriting return address. So those stuff you should try to save, right? So that's if necessary, right? And sometimes for V0 we don't do it because it's the return value, right? So that's why, except for V0, everything that we need to overwrite, we have to save it explicitly. So that's the convention in MIPS instruction set architecture. So except for MIPS, in a class we mentioned x86, not because it's good, just because it's widely used. So the concept of x86 is quite different in a way that the number of registers is a lot smaller, is half of them. And not all registers are equally long, and not all registers can be used the same. Like the RIP means program counter, the flags are additional inputs or additional states to instructions that the instruction would read or set. And they do have instructions, and they also have the move instruction for memory access. However, if you look at how the move works, is actually very complex. That the move instruction has tons of memory modes, and for a single move instruction, you can let it do read or store, right? You can use it to do load and store, and you can also use it to do like load immediate or even like add immediate, this kind of stuff, right? So it's really a very crazy instruction in x86 that you won't ever see in MIPS instruction set architecture. And another thing that I want you to remember is that we didn't talk a lot about the memory abstraction. However, in instruction set architecture, we do have the constraint of aligned memory access across all modern architecture, not just MIPS, not just ARM, but also x86, in a way that each object instance of data structure in a programming language occupies consecutive memory location, and they must all start with aligned with 8. And if it's x86 instruction set architecture, and the starting address of each member in the structure must be aligned with the multiple of their width. So saying that if I have a data structure or say a member that is 4 byte wide, then its starting address must be the multiple of 4. If its size is 8, it must be starting with the address of multiply of 8. So that's another thing that you have to remember, that we didn't talk a lot about in the textbook or in the class, but it's actually very important when you design your program, because if you look at this one, right, like the ID is 4 byte wide, so it has to start with an address that's aligned with 4, like 0, and that's aligned with 4. But when we move to the next one, homework, it's a pointer in 64-bit architecture, so it's 8 byte wide. And this address is 4, so you cannot have it start with here, so you have to have it start with 8. So if you keep iterating, you will figure out that this structure would take 40 bytes. However, if you can somehow rearrange the partition with the homework, you will see you can save 8 bytes of data storage in your memory, about 20% of your memory usage, which would help you a lot in saving the memory problem of your program if necessary. And we talk about both instruction. Okay, so Yizi, question?
Yeah, could you quickly go back to the this slide? So I just wonder if you can put the ID and participation in a single row, because they both occupy just half of the row.
Yeah, but you have to manually rearrange that. So
okay, so
if you swap these two lines, yes. But if you don't swap it, even though you have all compiler optimization turned on, no.
Okay, yeah, thank you.
Okay. All right. So And the reason why we want you guys to learn MIPS and x86 is not because I want you to write x86 assembly, just because I want you to feel the huge difference among them. And for MIPS instruction set architecture, everything is about 4-byte wide, 32-bit wide. But for x86, an instruction could be as long as, an instruction can be as short as 1 byte, but also as long as 17 bytes. So there are questions that I've been asking you about, like an x86 instruction can be shorter than a MIPS instruction, or it could be longer than a MIPS instruction. Both are correct because both are possible. And the addressing mode that x86 has is more. The registers that x86 have is fewer. And for and x86 also have tons of operations, right? So it has like 1,500 operations. However, for other modern processor instruction set architecture like ARM, RISC, or MIPS, we only have probably just like a few hundred operations that make this kind of computer called reduced instruction set computer comparing against the huge amount of instructions stored by x86. So those are the huge difference. Okay, so well, being honest to you, I know instruction set architecture is the most boring part, but thinking about the rest of the class, the rest of the lecture, a lot of examples, a lot of the hardware design is centralized by the instruction set architecture. So that's why we have to talk about it, right? And after instruction set architecture, we talk about performance, which you cared a lot in when you are programming your code, when you are running your programs. So it's really important for us to be on the same page about what is performance. So for computer architecture, when we talk about performance, if not otherwise mentioned, performance, the definition of performance is the flip, the reverse of your execution time. So the shorter the execution time means better the performance. So that's why its definition is like this. No matter you like it or not, the performance is defined by the reverse of execution time. And the execution time is calculated by total number of instructions within a program, how many cycles per instruction, and the cycle time. So, and the cycle time is usually the reverse of your frequency. So if you have a processor with a higher frequency, the cycle time is shorter, is smaller. And a very quick way to convert your frequency to cycle time is that if it's a 1 gigahertz processor, the cycle time is 1 nanosecond. And if you have a 2 gigahertz processor, the cycle time would be half nanosecond. So in this way, it should be easy for you to get it calculated. So the execution time, you might feel like I have to memorize it, but the thing is that if you understand how the processor executes instructions, then it's not that hard to understand. So again, the processor executes instruction one by one, and the processor is controlled by the clock. So depending on how many instructions that the program needs the processor to execute. And when we say how many instructions here, because it's a program in execution, so it refers to dynamic instructions. So how many of the dynamic instructions times how long is it take to execute each instruction on average? That's how you derive your performance equation. And using that is probably easy for you to understand why the answer of this question is A, just by calculating the average CPI, the total number of instructions and the cycle time, you will be able to get the total number of execution time. And speed up. I still see people asking about, okay, what's the speed up? So the speed up, there's only one definition in this class is if we say y is n times faster than x. The speed up is always execution time of x over execution time y. The speed up of y over x is indeed execution time x over execution time y. So you can replace y and x with anything. So if we say y is the new design, x is the baseline, the speed up of new design over the baseline is the execution time of baseline over the execution time of the new design. So that's the speed up. So given this, if you really want to calculate the speed up, you have to calculate the execution time of both. And then by using that, you can get a speed up. So for this question, its answer is not A, is not B, is also not C, is D, because that's how we calculate it. If you don't like it, I mean, that's fine, but you have to accept it. There are tons of things we don't like, but we have to accept it. Like if you don't like English, but you still have to speak it, right? Because that's a convention we define, right? So the same thing here is that the speed up is defined as what it is, and there is a reason why we do that. But you know, even though there's a reason, some people would say like I just don't like to accept it. But you know, if you want to get credits, just accept it. All right. So what makes the difference? So so that's another thing, right? So by knowing the performance equation, right, it's important for us to identify the limiting factor in in your execution time. And again, execution time is by instruction per program, cycles per instruction, and the cycle time. So if I have a program like this running on two different processors, and then one thing you will figure out is that, well, if it's the same instruction set architecture, the same program, the instruction count should be the same. And well, the cycle time, the lower cycle time, or say higher frequency, would drag the execution time down. However, for this case, it looks like AMD is using more time. So this is not the main reason why the performance is better for Intel processor. It's more about like we have lower CPI on Intel processor, and it's even a lot lower than the percentage of the cycle time of difference between the AMD and Intel processor. So that's why for this question we say Intel processor wins on the CPI, even though you guys might think the cycle time is different, but that's not that's why it's not cycle time is not the answer, right? So talk about so another factor that we mentioned in the class is that programmers is the most important factor in affecting the computer system performance. So we have been seeing this demo for many times, and for later on you learn just for the lecture yesterday, you know, like, well, the reason why this guy has more instruction count, but because of this line, but has better performance is because we have lower CPI. We know this for sure at this point. However, the reason why we have lower CPI is because the branch prediction accuracy is higher, right? So that's the magic of programmer, right? And compiler won't be able to do this for you because the compiler is to not make your program wrong. And if the compiler sorted it internally, the compiler cannot guarantee if your program is going to be correct or not. So that's why this kind of optimization has to be done by the programmer. And except for that, like so I keep saying that the complexity is like a junk because this is like a good example for you. Like both programs, they have the same complexity, the similar instruction count, and the clock rate for the same processor, they are the same. But the left-hand side would have a lot better CPI than the right-hand side because you know computer architecture, you know how the programming language lay out your data in a computer, in a processor or the memory you have in the abstraction. So the left-hand side code would allow higher access throughput for low store instructions. So that's why the left-hand side is better. And so in this way, this example also tells you that the CPI programmer effects. And not only just the CPI, the programmer also can affect the cycle time, which I also showed a demo in the class. By just using a script, you can do it, right? So everything programmer can affect. And programming language, a lot of you spend a lot of time thinking about what's the best programming language. But in my perspective, the worst programming language would be Java, because if you look at the instruction count, Java actually generated a lot and used the hugest number of line of code by human beings, right? So not good for you, not good for a computer. Why bother using Java? Well, Java has other advantages, but definitely not on the other not in terms of the performance, right? And if you want to reason about why the difference among programming language, here this slide tells you why, right? So for C programming language, we just pay the one-time cost in compiling your program, and the program is like an assembly language. It's just assembly language now. So whenever you want to run it, you just need to load the compiled program into the memory, and your processor can directly run on it. So that's a beautiful part about the compiled languages, because the compilation is just a one-time overhead. For Java, it does have the one-time overhead of generating code into Java bytecode. However, the Java bytecode is not real machine code. And instead, every time when you execute a program, the Java virtual machine has to translate the Java bytecode, which is usually a different type of architecture than your bare machine. So if you look at the machine, the MIPS instruction set architecture or the x86 instruction set architecture is typically a machine with registers and memory. However, if you look at the Java bytecode, it's just a stack machine, which now no architecture implements that. And because of the architectural mismatch, Java virtual machine needs a lot of effort to translate those stack-based code into machine code running on your real machine. So that's why it's so slow. So interpreter-based programming language does also have the every time overhead to translate from code to machine code. However, for the interpreter-based language, it's not that bad, because at least it's not translating from one extreme incompatible computer architecture to another kind of computer architecture. So that's why it's even faster than Java. So if you look at the programming language, it affects the instruction count and the cycle, the CPI. However, it won't be able to affect the cycle time as the programmer, because the programming language don't know if doing this is the programmer's desire. So that's why compiler cannot change that much. And by changing the instruction count, don't get it wrong in a way that lower instruction count doesn't always mean better performance, as we already proved several times through code examples. So compiler, again, it affects the instruction count and the CPI. However, compiler cannot do this for you, right? And even for this one, because compiler will not flip the order of the loop, because the compiler just doesn't know if it's safe. So so that's the reason why the programmer has to know this, otherwise the compiler cannot help you. So so there are tons of limitations on the compiler. So it's important for you to figure out like what kind of stuff compiler can do, what kind of stuff compiler cannot do. Harris.
Going back to the previous slide with the you know, the ints flipping. Can you go over again very quickly? Why is it that B is significantly slower than A?
So you will know this in after midterm when we talk about memory. But the short answer is because your programming language, well, most of the programming language, modern programming language, except for Fortran, everyone is laying out your memory in row major order. So this one goes through the memory in row major order, and this one will go through in column major order. And if you can consecutively access memory, and later on in the chapter, in a class, you know, there's something called cache in our computer architecture that would optimize for row major order access.
Thank you.
So it's because of the hardware optimization. All right. All right. So, all right. So compiler cannot do this for us, right? So you know compiler has its own limitation. So that's why we need to have a class like this to teach you how to make yourself a performance programmer. And a lot of computer scientists, they have the myth, like people who aces in CSE100, 101, this kind of algorithm class, they are the best programmer. But what I really want to tell you is that if you have someone who only knows the knowledge from CSE100 or 101, that's actually a disaster, because the computational complexity provide no insights of the real number of instructions or the real number of cycles per instruction that will be generated from your program, because the computational complexity is assuming that each instruction takes exactly the same amount of time, each operation takes exactly the same amount of instructions, which is never true, right? So that's why don't just trust computer algorithms or computational complexity. You should also know more about computer architecture. So here's a summary, and this is probably the most important part in computer architecture, that the performance is execution times reverse of execution time. Execution time is calculated by IC times CPI times CD. And who can affect everything? That's the programmer. And other stuff like programming language, algorithm, compiler, they can only affect two of the factors. And for the hardware technology, microarchitecture, they are effective for CPI and the cycle time. So so those are the things that you need to the important takeaways for the performance equation. So in terms of performance, there's another law in computer architecture that's also important, and there are not that many laws in computer architecture, right? Like the performance equation, the Moore's law, in which we don't even have a math of it, right? But Amdahl's law is not really a separate law. It's just a derived form of speed up that we had in previously, right? So Amdahl's law says that the speed up of your program should be like the fraction of time that an implementation can affect, and the speed up that you can achieve on the fraction of time that you want to optimize. So if you put this back in a scale that you make the baseline execution time as 1, and the fraction of time you can affect as f, and the enhanced part would be f over s, and the remaining part would be 1 minus f. So that's how we get this Amdahl's law. So Amdahl's law is nothing new. It's just a reshape of the speed up equation. However, it really gives us a lot of convenience in, first of all, if I just don't have the complete execution time, right? Like this Steam post, right? Some people saying that, well, I ran again on a hard drive and it takes so much time, right? And if you dig out another paper, you will figure out that when you are loading a map, 95% of the time is on the hard drive, and the rest of the time is software overhead that your processor would deal with. So you know, if I have a flash drive, or say an SSD, which would be 100 times faster, I'm not bluffing you, right? So 100 times faster by an SSD, that's possible, right? But it's just 100 times faster on the 95% of the time. So if you put that into MDOS law, you will figure out that it sounds like you have the intuition that if somebody says that this time is 100 times faster than your original one, and 95% of the time you are spending time on this part. So you think, well, my speed up should be close to 100 times. However, if you use MDOS law, what you really feel is only about 17 times faster, which is far away from that 100 times. So MDOS will give you a very good idea about like what's the effective overall synthetic speed up I can get in my whole program, so that you won't be fooled by the mass of business guy, because they always tell you that, okay, Flash is 100 times faster than your hard drive. So put this in your computer, your game will be 100 times faster. That's a lie, because if you use MDOS law, it's never like that. However, even 17 times is already fast enough for you to feel, or at least give you like 1 second ahead other people, right? So that's still worth it. But most of the time, the math is not like that simple, because your program consists of multiple parts, and multiple parts can be optimized separately. So if you can extend the MDOS law to do this, but just one guideline: make sure that you have to make a chart with this non-disjoint part and apply the speed up of each non-disjoint part like this to calculate the final result. So say right now, okay, if I'm rich, then not only I can get a new solid state drive, I can also update my processor with the latest like AMD Ryzen processor, which will give me like twice speed up in the processor part, right? So then what would happen is that both the 95% of time and the 5% of time would get speed up. So the 95% of time would get 100 times speed up from replacing the hard disk drive with flash, and the processor part would get speed up by getting because of the replacement of the processor. Now we get it closer to 29 times, right? So so even though the processor improvement is incremental, but if you are rich, right, then still getting a faster processor will probably help you a little bit, but just not as significant as what what other parts will give you. So here gives us the first MDOS law's corollary, is that the maximum speed up is bounded by the 1/1 minus f. And we derive this is because we can put infinite in your S part. And by doing this, you will figure out that's the maximum speed up you can get. So if somebody is asking you like, okay, I want to get, so somebody is asking you right now, I want to further achieve twice speed up. And what I want to give you is that, okay, so give you this guy, right? Like I want you to investigate in newer memory technology. And by using newer memory technology, our goal is to achieve twice speed up in loading maps, right? And if this is what your CEO asks you to do, I think that the message is clear that, okay, he really wants to lay off your whole group, because it's impossible by just improving the 16 part of your system to achieve twice speed up, because the maximum part that you can achieve is only 1.19, right? So it's never possible to achieve twice speed up. And even though you want to stay in a company, you still, I guess another thing that you want to do is that you really need to think about, it's not you leave or you just make your company fire the CEO, because the CEO doesn't even know what he's talking about is not possible, right? So if you have MDOS law, if you know this corollary, it's very good for you to easily estimate if it's possible to do this to achieve my goal, right? So another corollary which we can get from there is that if you get the maximum optimization from each part, you will know if I can only do one thing at a time, if I have limited budget, then I should just use it on the part that can give me the maximum potential of speed up, right? So for this case, right, if I can only do one thing, then I will probably pick F4 because it looks the largest, right? So here comes to the second corollary is that focus on the common case and make it fast, right? So, but when we say the most common case is the most consuming case, all right? So, and how to identify it, a good tool is gprof, right? So we have demoed how to use it. So check that from the YouTube video. And if you, another thing that I want you to keep in mind is that optimization is a moving target. So one thing I really don't like is that people never update their knowledge. So there are always guys in the data center or some company, they keep telling you that, okay, we want to optimize the computation part of our system. But the answer is that, guys, the world is changing, right? And because you guys have been keeping optimizing the processor so much, so the most important thing is changing, right? So what we see here is that if you, after you optimize your CPU algorithm a lot, the next thing to optimize might not be the CPU, because if you put it back on this chart, the most significant part may be the storage media. Like what we just saying in the previous example, that when you optimize something, the most significant thing will keep changing. And another drawback of just focusing on based on your own knowledge is that, well, people would like to optimize something, but ignoring the side effect that the optimization might have on other parts. So like this example, if you, it sounds like optimizing a program spend in 90% and achieve 9 times speed up is a good idea. However, what if it hurts other part by 10 times and it turns out it would give you slowdown, right? And for Amdahl slow, it has some kind of limitation here, is that for Amdahl slow, the overhead is hidden and it doesn't bound to slow down. So there's another law in computer architecture that we didn't talk in this class would deal with that. But I think for now, Amdahl slow and the performance equation will be good enough tool for you to use for performance programming. And there are other implications from Amdahl slow, which I do want to mention again, and especially this is a word of parallelism, as you have heard many times from our opening video, that single core processor is not getting any faster. The future is parallelism, right? So if you have a GPU right now, you already have a processor with thousands of LU, or say parallelizable processor within that GPU. Right, so the future is parallelism. So if you use Amdahl slow, what you would derive is that the speed up is bounded by the fraction of parallelism that you can find in your program. So, and if you can make the parallelizable part, if you can have unlimited number of processors, then how fast of each piece in the parallelizable part is not important, because it's all divided by this infinite number. So so it tells you that the complexity is a junk again, because it's more important that you can make your algorithm parallelizable than seeking for lower complexity. Because if you have a low complexity algorithm, but you cannot evenly divide it to this infinite unlimited parallelism, then the algorithm is junk in the future, right? So that's another takeaway, and actually one of the very important takeaway for the class. All right, but how do I know this? It's all based on Amdahl slow. Another thing is to make your comparison fair. And so a lot of game companies, or even like companies that talking about machine learning a lot, they don't like to use fair comparison because they just afraid of using it. You will discover the lie that they make, right? So one of the biggest alike, which NVIDIA uses a lot, or a lot of game company uses a lot. Like if you just look at the table, you will figure out NVIDIA produced the best gaming machine. Microsoft produced the best gaming machine. However, that's not the truth, because T-flops, which is the benchmark, which is the metrics they presented here, if you just go through the equation, it just eliminate the instruction count, which is a very important factor in computer architecture, because different machine, they have different instruction set architecture, have different compiler. And it doesn't make sense for an application that is floating point intensive to also use T-flops to evaluate the performance. So for example, like a lot of your machine learning inferences are based on integer calculations. So you tell me that I have a machine learning accelerator that is really good at T-flops. Okay, sorry, that's a junk, right? So that's another thing that you need to know, that fair comparison, right? So choose the right metric, that's important. And another thing that people would always get confused about is the latency versus the bandwidth. So latency is the amount of time of finishing an operation. So access time, response time per operation, that's the latency. Throughput is the amount of work can be done within a given period of time. So when you see bandwidth, IOPS, T-flops, they are all about throughput. However, this graph should give you a very good idea about the difference between bandwidth and latency. So if I want to transfer 2 petabytes of data using the gigabit network is not giving you the best latency bandwidth. However, the response time, or say the latency, is a lot better than using a Toyota Prius, because if you use a Toyota Prius, you don't see anything within 3.5 hours. All right. So processor design, that's what we are at now. And a lot of you focus on hardware a lot, but I would like to put a hardware stuff on CSE141L to make your life easier. However, this big picture, what we do with dynamic instruction is really important. And I don't require you to understand every single signal in the processor, but I do want you to at least know what each part of the circuit is doing. So if you look at this single cycle processor, you need to at least know this is instruction fetch, this is instruction decode, this is execute, this is data memory access, and this part of the logic is for write back, and this part of the logic is for the next PC. So when we partition your processor with pipelining, right? Like, okay, you will know that why I say that. Well, if it's a branch instruction, the outcome has to wait until the end of the execution stage, because the branch target PC is calculated here, right? So that's what I all want you to know. I don't think it's a very I don't think it's a very overly request, right? So that's all I wanted to know. So do take a look of the pipeline diagram, circuit that I spent a lot of time to draw, and I only want you to know the high level part, right? And as we said, the single cycle processor is slow because it has a lot of drawbacks, that the cycle time has to be aligned with the longest latency, the instruction with the longest latency. So we use another idea called pipelining. So the pipelining is that different parts of the processor work on different instructions simultaneously, and the clock signal controls and synchronize the beginning and the end of each part of the work, and the pipeline register between different parts of the processor to keep intermediate result necessary to the upcoming work. So as you can see, for pipelining, your circuit is separated by pipeline registers, and each pipeline register is connected with the clock. And for each clock signal, the circuit only needs to complete a stage of work for the given instruction. and propagate it through the pipeline. So if your pipeline goes smoothly, what you would expect is that every cycle you would get one instruction output, and the CPI is always 1. And the cycle time of the processor is decided by the critical path, or say critical stage in the pipeline. So that's why, given the original design like this, for this processor, you can have to fix the cycle time at 3 nanoseconds, and the maximum speed up use the equation we gave you can only be 3.33, right? And so here comes the limitation of the pipeline. And but that's not the worst part of the pipelining, right? So the worst part of the pipelining is that, well, okay, so before we talk about that, right? So the good thing about pipelining is that because we can pipeline all the instructions, so and we make every instruction equally long for the pipelining, because we want to avoid the structural hazard that you later on learned, right? So for this pieces of a code, some of you, if you just have the memory from CSE30, and your professor probably don't even notice this, so he keep teaching you about this, right? But the truth is that with modern pipeline processor, because we make every instruction equally long in a pipeline, and the cycle time of an instruction, the cycle time of the processor is the same, and the processor just keep outputting an instruction per cycle. So the left-hand side code and the right-hand side code, like the average latency for executing this multiply would be the same as the average latency of executing the shift. And in fact, because the right-hand side give you higher instruction count, so that's why when we have the demo, the right-hand side actually has slightly slower than the left-hand side, because of the instruction count get increased, right? So, however, most of the time, you are going to interface with pipeline hazard, like what we show up here. And there are 3 different types of pipeline hazard. And how do I know if I have a pipeline hazard or not? The only thing you can do is to draw the pipeline diagram. So I have talked about how to draw the, I think there's a slide somewhere. Oh, shoot, how come I don't have that slide? So refer to my slide regarding, oh, here we go. So this is a very important slide. So we have a lot of questions, a lot of homework question regarding how to draw a pipeline diagram. So here is it, right? Every instruction needs to go through 5 pipeline stages, because of we want to avoid structural hazard. So every instruction needs to have all 5 of this. And an instruction can enter the next pipeline stage in the next cycle only if no other instruction is occupying the next stage. The instruction has completed its own job at the current stage, and the next stage has all its input ready, and it can retrieve those inputs. When I say this, it means data forwarding, right? So these are the three guidelines regarding if we can move to the next stage. And we can only fetch a new instruction if we know what's a new instruction, right? Or if we can predict it, right? And if we have misprediction, flush the instruction. By flush, it means that beyond the point that you discover that you made it wrong, just made them no ops, right? So that's the tip of, that's the 3 guidelines of drawing the pipeline diagram. So after drawing the pipeline diagram, you'll figure out for these 4 examples, they all have hazards. And this hazard, they maps perfectly to these 3 types of hazard. 1, structural hazard, meaning that the pipeline doesn't allow concurrent access to the same hardware unit of different instructions. We also have control hazard, means that the PC can be changed by an instruction in the pipeline, which means that we don't know for sure what's the next PC. And sometimes you have data hazard is because of the data dependency is not yet resolved or propagated through the pipeline. So if you look at these three pieces of code, they actually represent different types of pipeline hazard. And to deal with structural hazard, usually the best way is to modify your design, right? So install would help, however, it's just so slow. So another option we have is like we just modify our register hardware to allow concurrent access. Or another reason why we always need to have 5 pipeline stages, even though like instruction, like branch instruction, we don't even need the last 2 stage, just because we want to avoid a structural hazard. And it also explains why the code example that I just gave you, using shift and using multiplying. And it sounds counterintuitive because multiplier takes so much time. However, because of if both instructions, they share the same integer instruction pipeline, even though multiplication takes more time, it doesn't affect the CPI of your shift instruction because they are all within the same pipeline, right? So that's the reason. And another type of data hazard is called data hazard. And data hazard is because of we have data dependency, and the data dependency cannot be resolved because when we need the input. And the data dependency is the output of an instruction is the input of a later instruction. And it may result in data hazard, but not every data dependency leads to data hazard, right? So for this question, we have 3 data dependencies. But if you really use stall, then every data dependency will become data hazard. However, if you have data forwarding, then only one of them would cause data hazard. And the reason why there is still a data hazard is just because for the low word instruction, we have to wait until the end of memory stage. So if you have another instruction, depending on the load instruction, you just have no choice to wait. So that's the only data hazard that you will see with a processor support data forwarding. So you need to add additional hazard detection units for that case. So, and this also explains another code example that I gave you why if you have your index coming from a load instruction and the calculation result, depending on the load instruction, it has to wait for that long time, and then the multiplication does hurt. It's just because of the data dependency, right? So this is the resulting hardware of data forwarding. So if you in your test you see this graph shows up, it just tells you that you have a processor that supports full data forwarding. So if tomorrow you see this figure in your question, this is a processor with data forwarding. This is a processor with hazard detection. It's just that you can safely draw a pipeline diagram like this if you are given a processor like this, right? So this is what you have to pay attention to. And if you ask me, hey, professor, this question doesn't tell me like if this processor has full data forwarding or not, I won't answer you because I already gave you this diagram. And if this diagram is in your question, it's your duty to understand there are elements here to help me resolving the data forwarding to detect the data hazard. And this is the pipeline diagram that I should derive, right? So that's why you need to understand those. Control hazard is the case that we don't know what's the next PC to fetch. And in the MIPS 5-stage pipeline, so some of you might ask me, like, how do you get this? How do I know I have to stall for 2 cycles? Again, look at the pipeline diagram, as I mentioned, because the branch target PC is calculated here. You got your LOU outcome for the branch result here. So there's no way you can know what's the next PC for sure before the execution stage of your processor, right? And if you want to do branch prediction, 2 things you need to know: the target address, which we make a branch target buffer, And the second thing is the branch outcome. So that's why we have the predictor. So if you just don't want to use the branch target buffer, this is the best you can do. You can only statically predict not taken. And for the frequently used loop, you can only have 25% accuracy, which is not a bad thing, right? But if you have a dynamic branch predictor, like the local predictor that I presented here, that we train the state for each PC locally, and you will see that you will have 75% accuracy for this piece of code. However, 75% is not perfect. So we have the global predictor, which utilize the pattern of all branches. So with this, the pattern is the states are decoupled from your branch target buffer, and the states are trained by the global history register. So when you see if I currently have a branch instruction, I use the target PC as the predicted PC. But to predict if it's going to be a taken or not, I use the global history register as the index to access a table of states. And each states are trained separately based on the last time when I saw this global history register value, if it's taken or not taken. However, the way how we train those states are the same as the 2-bit saturate counter algorithm that we discussed previously. So that's the global history predictor. And it's important for you to know how under what situation which one is better, under what situation which one is better. And the truth is that modern processors, they invent mechanisms to combine both predictors. So that's why I told you guys both. And as a programmer, it's very important for you to figure out your impact on programming, and not just those grandfather old knowledge prior to 1995, but with the modern pipeline processors. So as you can see, if you only know instruction count, then you might think C is the best. However, if now you know there is something called branch, and you know the compiler can do loop unrolling, then you will figure out that the D version is the best. And it gives you the lowest instruction count. It avoids all the branch instructions. And you see a lot of memory accesses. However, later on, you will know that the memory hierarchy, especially the cache, does give us a huge optimization on these pieces of code. Okay, you are here for a reason because of that, the midterm. So here's the logistic of the midterm. First of all, no cheating is allowed. Make sure that you have a stable stable internet connections. And the reason why I'm saying this is because for Canvas, once you disconnect it, you are automatically submitted, and you are not allowed to restart it. And there's no guarantee that we have the access right to reinstantiate that. And even though we do that, the only thing we can do is to clear your previous to reset all your previous efforts. So if you don't want to waste your time, just make sure that you have stable internet connections. Some people were asking about, do I need to have a webcam? Well, if you have a mobile phone, you can still install Zoom on a mobile phone, and you have most of a mobile phone has a camera now, right? So you can just have the camera facing you. I'm fine with that, because all I need to do is to make sure that you are not having somebody else besides you to assisting you, and also make sure that you are maintaining good social distance with your classmates, right? So that's why we want to use Zoom to protect. Some people keep asking about, like, can I open my slides? Okay, so here's the thing, right? If you are using Zoom, you are facing your webcam. What are you doing with your browser? Actually, I cannot know, right? So I just don't bother having you watching a slide. But the thing is that if you are not familiar with the slide, you will figure out that the number of questions we have is probably good enough for you to not having time looking up your slides. So you still have to study, right? Look at that. The format is 20. So your textbook is it's PDF format, sure, use it, search it, do whatever, right? But we have 24 questions, and each of the 4, they have sub questions. So you only have 2 or 3 minutes on each question. And if you spend too much time looking for slides, looking for textbook, you don't have sufficient amount of time because the test is only about 18 minutes long. And because we want to make sure that your environment, so make sure that you join by 1:55, and I will lock the room after 1:55, means that if you cannot get in on time, I won't be able to allow you to take the midterm. All right, so here's a sample midterm. We have 20 multiple choice questions like this, and you know, like, so, and then we also have questions like this, like asking you why. And Amdahl is important. Definitely, we will let you practice. And draw the pipeline diagram. That's important. So we will definitely ask you to draw. And dynamic branch prediction. I spent so much time talking about global predictor, right? So I really want you to know, like, for different pieces of the code, how different predictor would act like. And but you know, there are other things to think, like performance equation. How can you practice performance equation, right? Implications of Amdahl's law, that's very important, right? Instructions and like, what's the difference between MIPS and x86? I have a lot of demos, right? I do want you to take a look at my demos, right? And why we say, like, people using T-flops, they are lying, right? And why a single cycle processor is not working, right? And like, what are the pipeline hazards, right? And how to solve those pipeline hazards, right? And the code optimization that I show you, right? They are important. All right. So these are the bits that I would say, right? So if you have any question, please raise your hand. If you have any question, please raise your hand. I don't answer other questions. Okay, Richard.
Hey, Professor, could I just clarify something? So we're fine while we're taking the test to look at slides on our computer, the book on our computer, change the tab, even though we might not have much time, we're allowed to change the tab and all that.
I mean, I cannot know, right? So if there is something that I cannot know, then I would just allow it.
Well, I only ask because, like, is the test through Canvas? Like, Canvas tracks whether we switch off tabs and all that. You know what I mean?
I don't think they do it. I don't think they do it. All right. Onward, how can I help you?
I was just wondering, out of your experience, what would you estimate like a reasonable average time for the free answer? I'm probably just going to do that part first, but you know, it helps to, you know, organize my time so I don't get like hung up on a question.
Well, as I said, right, the whole midterm is designed for 18 minutes long. And sometimes you think free answer question is taking more time, but sometimes multiple choice questions would probably take more time than that.
Okay.
So
I'll keep it in mind.
on average, I would say probably 2 to 3 minutes per sub question.
Oh, okay. All right. Yeah.
Okay.
Cool. Thank you.
Okay. Okay. So Yue Chen, how can I help you?
So you said if you don't know, like, if we're switching tabs or not, then what's the purpose of the webcam? Like,
so the webcam. So the webcam is protecting. At least you are not discussing with others.
Oh, I see. Thank you.
Right. You are not discussing with any others in person. That's the only thing I'm not allowing. Right. All right. So, Kun Yi, question.
Yeah, hi, Professor. I have a question. Like, can we use the iPad to access lecture slides?
No.
So we can use iPad, right?
So the thing is that you will use your camera to look at your surroundings, right? So everything other than your camera, your mobile phone, and that's not allowed, right?
So you just said we just allow like discussing the midterm like in person.
No, you are not allowed to discuss.
Yes, I know. Just want to make sure if we can use iPad to see the slides. Yeah.
I mean, what can I say? I prefer not. Okay.
Okay. Thank you.
All right. Onward. Question. You are unmuted. Okay.
Yeah, just adding on to that. I have pretty useful like handwritten notes. Can I just have that out?
I mean, can you export it to the PDF on your computer?
Probably not. It's like a pretty dense notebook.
What do you mean?
Like, I mean, like sometimes like I handwrite notes in like a specific notebook for the class, and that's probably actually faster for me than to go through the textbook or slides. Can I have that out?
Oh boy, what can I say? I mean, all right. So what can I say? So, okay, so Queenie, if you want to use iPad, okay. If you want to use your notebook, yes. But when I check, okay, so first of all, when I check your environment, if there's anything I feel like that is suspicious, even though I say yes now, if I don't feel comfortable that you have that in your environment, you have to take it away. Is that okay?
Oh, okay. So in that case, like I'll show you my notebook or something.
Yeah, something like
decide,
that.
Yeah.
Okay.
Okay. Sounds cool.
Okay.
Yeah,
cool.
I understand. Yeah. Thank you for being accommodating. Appreciate it.
Okay. Other things. Okay, if not, before you leave the classroom, there are a few things I want to let you know. First of all, join the Zoom meeting by 5 minutes before it starts. And reading quiz, there's one due next Monday. So a lot of you asking about like, okay, assignment 3 is too rushed. And actually, I think some of the Piazza post is unfair because I actually post assignment question very early on the website. And the reason why I didn't enable that in Canvas is just because people keep saying that I submit the assignment to the wrong place. So that's why when I never mentioned that you should check Canvas for assignments. You should check our website for assignment questions. Harris, questions? Harris. Okay, so so some people that okay, so if you are suffering the blackout because of the electricity issues, if you can give me your address or some kind of evidence like a screenshot of like Edison, like Southern California Edison or SDG or what else electricity company showing that your area, your address is currently blackout, we will think about how to deal with that. But the thing is that, as I said, if you know this ahead of time, and I don't think they are going to give you the blackout without any warning, you should still be able to find a place to prepare your to have your midterm. So I won't. I technically, as I said, right, the time is scheduled, and you should be able to find a place. And so unless it really happens, we cannot really. I don't feel like it's possible to accommodate that situation because this is summer session. The course is really short, and there's not really a lot of slacks for you to for us to accommodate a lot of accidents. All right. So, all right. So the thing is, and if you don't feel like you can get the assignment 3 done before the deadline, that's okay, because we drop your latest assignment, your lowest assignment grades, right? And the TA is supposed to publish the solution right after the deadline, although sometimes she didn't. But I don't have the solution. She has it, so push her to publish that. Other than that, I think that's everything you need to know before the midterm. I will see you tomorrow on Zoom again.